Okay, so let's do the calculation of this. And we'll see from this calculation why it is that these two cases work exactly the same. So the example, so let's say that an object is first dropped and second shot horizontally we have to give it a horizontal speed, let's say 1,000 meters per second. That's somewhere in the ballpark of how fast things come out of a gun. From a height of 1 meter. How long does each take to hit the ground? Okay, so first we're going to do it for the case where it's just dropped to the ground from 1 meter. We can just do that as a one-dimensional kinematics problem because we know that the path is just straight vertical. Okay, so if the object is dropped there. That's supposed to be a hand. Okay, so this object's just dropped down to the ground. The initial height is 1 meter. The first thing we have to do is choose the time equals 0, the time final, the 0 position, and the positive direction. Let's put the 0 position on the ground and the positive direction up. We don't have to do that, but and time equals 0 is going to be when it's dropped. And time final is when it hits the ground. And now we have to think about what variables we know and what variables we want. Okay, so time final, we don't know that. That's what we're trying to calculate, the amount of time it takes to hit the ground. The acceleration it's free fall, so that's down at 9.81 meters per second squared, and down is negative in this case. The initial position, the height of the ball when it's dropped, is 1 meter in the positive direction from 0, so that's going to be positive 1. The final position is the ground, so that's 0. The initial velocity is the velocity of what it's dropped from, and that's not moving, so the initial velocity is 0. And we don't know the final velocity, but we're not looking for that. And we can use that in the equation that says PF is equal to PI plus VI TF plus 1/2 A TF squared. And so 0, I'm going to leave the units out of this calculation. 0 is equal to 1 plus 0 times time final is 0 plus 1/2 times negative 9.81 times TF squared. And if you move that second term over to the left side, you get 4.905 TF squared is equal to 1. So TF squared is equal to 1 over 4.905. And so TF is equal to plus or minus, I think it's 0.455 seconds. That's two possible times. Which one do we want, the plus or the minus? We only want positive times, so it's going to take 0.455 seconds to hit the ground. Okay, so that's if it's just dropped. So now let's see mathematically what it says is going to happen if the ball has a horizontal velocity of 1,000 meters per second. Okay, so this is A. Okay, so now here's the gun. It's like a dirty, hairy gun. And so this time the bullet will be shot horizontally. The height is 1 meter again. For 2D kinematics, well, we have to choose the time equals 0 and the time final, and those are going to be the same as they were before. Time equals 0 is going to be the instant when it's shot. Time final is going to be the instant when it hits the ground. And then I'm going to do what I said I think I pretty much do all the time. I'm going to put the origin on the ground underneath the object at time equals 0. So that means right underneath the point where it's shot from. And I'm going to put the y-axis pointing up and the x-axis horizontal in the direction of motion. So these are just both shown in the picture. And now we have to think through all the variables. So first time final, again, that's what we're trying to find. Acceleration, AX is 0, AY is negative 9.81. P initial. So for P initial, we're talking about at time 0, what are the coordinates where the object is, the bullet? It's 0x and positive 1y. So PIX is 0, PIY is 1. Then the final position, it's going to be on the ground. We don't know how far out it's going to be. So we don't know PFX, but we know PFY is 0. Then the velocities, initial velocity, so VIX and VIY, we're going to know both of those. And the reason we're going to know both of those is because we know the initial velocity has a magnitude of 1,000, and it's completely horizontal. so if you put the tail of this 1,000 meter per second vector at the origin, we're trying to calculate the coordinates of the head. And so if you go out a distance of 1,000 along the x-axis, what are the coordinates at that point? Yeah, positive 1,000 for x, 0 for y. And then we don't know anything about the final velocities. Okay, so is there an equation that works with this stuff to let us solve for time final? This one works. PFY is equal to PIY plus VIY PF plus 1/2 AY PF squared. And we'll see when I fill this in, it's just the exact same equation we got before. What's happening in the x direction just doesn't, mathematically, it doesn't come into it at all. So this says 0 is equal to 1 plus 0 plus 1/2 times 9.81 times TF squared. And that's exactly the same equation as we got in part A. And so when you solve it, you get the same thing. Time final is equal to plus or minus 0.455 seconds. We only deal with positive times. And so when you look at the math, you see where that, I mean, this doesn't really explain, like, if you trust that these equations describe what's really happening, you can see why mathematically there's no connection between the x and y. If you're using an x component equation, well, in this case, we're using a y component equation. There's nothing in here that's an x component of anything. This doesn't, there's no relationship between those. So whatever is happening in y is totally independent of what's happening in x. Yes? Why did you put 0 for ax? Is it because they don't care? Or excuse me. I did that because, so first of all, that if you always put your y-axis of your coordinate system up, then the components are always going to be ax is 0, ay is negative 9.81. And you can see why that is if you draw the coordinate system. And we know that gravity, what gravity always does is accelerate things in free fall down at with a magnitude of 9.81 meters per second squared. So draw that vector with its tail at the origin. That's in the negative y direction. And so if you're trying to come up with the coordinates of the head of this vector, you know, what are the coordinates of this point here? 0x, negative 9.81. Well, yeah, that's velocity. So remember, when anything's in free fall, if an object's in free fall and there's not significant air resistance on it, then the acceleration is always just 9.81 down. I think the fusion is, it's easy to mix up. You're thinking about velocity with acceleration. So the thing does have a horizontal velocity, and we put that in here. Its velocity vector is horizontal with a magnitude of 1,000 meters per second. But if something's in free fall, its acceleration is just straight down at 9.81, no matter what it's doing. you have any other questions about that? Can you clarify that question at all? Or so I mean that's the for every free fall problem that we do, that's kind of the main thing is that no matter what's going on, if you shoot it up or sideways or down or whatever, those initial velocities can change, but the acceleration, what gravity does to it is just make it accelerate down at 9.81. Okay, it's my guess is that it's sort of hard to unwrap what velocity is and what acceleration is from each other. And we're going to spend a lot of time in labs trying to make sense out of that sort of intuitively. But nope, never in this class. The only way that we would have different accelerations than those for a free fall problem is if we chose a funny tilted coordinate system or something. But always for free fall problems, the acceleration is straight down at 9.81. Any other questions about this? Okay, let's do one more related question. So now, what if, shooting this bullet perfectly horizontally is hard? Each gun I draw, I'm getting better at it. So let's say that instead of shooting it horizontally, let's say that the shooter is trying to shoot it horizontally, but he shoots it up at an angle of 1 degree above the horizontal. That's a pretty tiny angle, It's a lot smaller than that angle I drew. I just can't draw it any smaller than that. So let's say that this angle is 1 degree. Yes. So now how long will it take for the bullet to hit the ground? So it's being shot at 1,000 meters per second again. And let's do a second one. Let's figure out what the highest point is in the bullet's path. So it's being shot up a little bit, so it's going to go a little higher than 1 meter above the ground. So what's the bullet's height? The highest point. Anybody have any intuition about these? You think it's going to be a lot longer or barely longer to hit the ground? And do you think it's going to be 1.05 meters or do you think it's going to be 10 meters? You have a feel for what's going to happen on this? No? Okay. Well, the answer is even though that's a very small angle, um, the bullet's going so fast that it's going to take a lot longer to hit the ground. I can't remember how much longer, but a lot. Um, and the bullet height is going to be high uh, because, well, let's just see how it works. Any questions about what I'm asking before I start doing this calculation? Bless you. Okay, so first we want to calculate the elapsed time for it to hit the ground. And we have to make those 4 choices. Time equals 0 is going to be when it's shot. Time final is going to be when it hits the ground. And then these I'm just going to show on the picture. Okay, so I'm going to put the coordinate system on the ground right below where the bullet is when it's fired. And the y-axis points up. And then we'll go through, calculate what we know and what we want. Time final per day. Acceleration is straight down, so AX is 0. AY is negative 9.81. Initial position is 0x, 1y. Final position, we know that the y component is 0. We don't know the x component. We could calculate that, how far away it would hit, but we don't have that yet. Then the initial velocity. We're going to know both of these. We have to calculate them. And the way we're going to calculate them is, let me take an angle. Well, that's still a lot bigger than 1 degree, but we'll put the tail of the vector at the origin of the coordinate system. And we'll say this angle's 1 degree. We know the magnitude of that vector is 1,000. And so the components of the initial velocity vector are the magnitude times the cosine of 1 degree for x, and the magnitude of 1,000 times the sine of 1 degree for the y component. Can someone calculate that? I don't think I have that here. So 1,000 times the cosine of 1 and 1,000 times the sine of 1. 999.8 meters per second. So you can see how close that is to 1,000. Almost all of that velocity is in the x component. It's almost completely horizontal. Okay, sorry, and then the y one? 17.45 meters per second. Okay, and so using sine and cosine, you get these values. And the thing is, so this one's almost 1,000, right? You might think that this one's going to be 0.2, but that's not how sine and cosine work. And so what we have here is that the bullet's going so fast that even though it's almost entirely horizontal, it's still vertically going 17 over 17 meters per second up when it's released. Okay, 17 meters per second up is over 35 miles an hour. Okay, and so what we're going to see, I mean, since the x and y motions are independent of each other, you can forget about this and just think, how long would it take for something to hit the ground if you took it at 1 meter up in the air and threw it at 35 miles per hour up? It's going to go way up into the air, and it's going to take a long time before it turns around and comes back and hits the ground. And so that's what's going to happen here. Even though it's only off of horizontal by 1 degree, a tiny amount, it's going to it's not going to be 0.456 seconds. It's not going to be 0.5 seconds. It's going to be many seconds. And the highest point that it's going to reach is going to be way, way, way higher than 1 meter. Okay, so VIX, I'll put here is 999.8. VIY is 17.45. We don't know anything about the final velocities. And now look for an equation that has TF in it, and everything else in it is known. And it's the same one that's going to work again. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. Now plug in our values. 0 is equal to 1 plus 17.45 TF plus 1/2 times negative 9.81 TF squared. And you can rewrite that as 0 is equal to negative 4.905 TF squared plus 17.45 TF plus 1. How do we solve this equation? Yep, quadratic. So that's A, that's B, that's C. Is there anyone in here who has this on their calculator already, the quadratic formula? Oh yeah, could you punch that in? Okay, so we don't want the negative time, so we want the positive time. No, we don't want the negative, we do want the positive. And so instead of taking 0.455 seconds to hit the ground, it takes 3.61 seconds. And then for part B, now we want to figure out how high it is at the highest point. So our time equals 0 is still going to be when it's shot. Our time final, now we have to change this one because we're looking for information when it's at its highest point. So this has to be at the instant that it reaches its highest point. The origin location and the coordinate system orientation, I'm going to keep those the same. And now we'll think about what we know, what we want to find. We know time final. We just calculated a time. But that's not the right time. You know, that's the amount of time it takes to hit the ground. We're looking for the time it takes to get up to its highest point. So we don't know that. We still know the acceleration. AX is 0. AY is negative 9.81. The initial position, we know. PIX is 0. PIY is positive 1. The final position, we don't know how far it's gone horizontally when it gets to the highest point. And we're looking for how high it's vertically. So PFY goes over here. PFX doesn't go anywhere because if we don't find that, that's all right. We're not looking for that. The initial velocity is the same as it was before. So 999.8 is the x component. And the y component is 17.45. And then do we know anything about the final velocity? We know that the y component of the final velocity is 0. That's how we specify that we're looking for the highest point. So VFY is equal to 0. That's always true when an object's at its highest point in its flight. Okay, so is there an equation that works with this stuff? I think this one should work. 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So we have 2 times negative 9.81 times the quantity 0 minus 1 is equal to 0 squared minus 17.45 squared. So the left side of the equation says 2 times negative 9.81 times negative 1. That's negative, nope, positive, negatives. So positive 19.62. Darn it. This is not 0. This is the thing we're trying to find. Okay, so this is PFY. So we have, okay, let me do this in steps. So 2 times negative 9.81 is negative 19.62. And we have that times PFY minus 1. And that's equal to, what's 17.45 squared? 300 what? 304.5. And that's negative. And multiply, so we have to multiply that negative 19.62 times both of the things in parentheses. So that's negative 19.62 PFY plus 19.62 is equal to negative 304.5. And then subtract 19.62 from both sides. So you get negative 19.62 PFY is equal to negative 324.1. Random significant figures, just like I like it. And then divide both sides by negative 19.62. And what do you get for that? 16.5. So just from shooting the bullet 1 degree above horizontal, before it falls back to the ground, it's going to get up to a height of 16.5 meters, which is like 50 feet. Minus the 3 feet that it's shot from, so say 47, it's going to go 47 feet higher just because of that 1 degree difference. And the reason, like to make sense out of that, it all comes back to the y component of the initial velocity. Any questions about that? Okay. Let's do one more. Um, okay, so let's say uh, you're on your bicycle. That's a sweet bike. And you're holding a ball, ping pong ball or whatever. Well, I guess something heavier than a ping pong ball so it doesn't have much air resistance. Okay, and now the rest of the bicycle. Let's see. So, um, it's going to go sort of like that, that. Your foot's probably on a pedal of some kind. There's a wheel, another wheel. Are you drawing this? You probably have racing handlebars. You look pretty fit. Okay, so here's you cruising along on your bicycle. You're bald now. And you're holding this ball 1 meter above the ground. And over here is a cup. And you're riding your bike 5 meters per second this way. And you want to know, you're holding this ball exactly 1 meter above the ground. Oh, and the cup has a height of 0.15 meters. How far away from the cup you have to let go of the ball, drop the ball, for it to land in the cup? Okay, so basically, like you know the speed that you're going to be biking along, and we're going to see if we can calculate what the horizontal distance should be between the cup and the ball when you let go of it. You know, if we calculated, you could put some tape down on the floor and do it, and get your friends at a party or something. You can do this. Any questions about the problem? Okay, so the first thing we have to do is choose time equals 0, time final, and then the coordinate system, the origin and the orientation. And time equals 0 is going to be when the ball is released. Time final is going to be when it reaches a height of 0.15 meters. And the coordinate system is going to be on the ground right beneath where the ball is dropped from. And the y-axis is going to be up. Oh, excuse me. So now we have to list out what we know and what we want. Do we know the amount of time that it's going to take for the ball to land in the cup? No. If we can do it without calculating that, that's fine. So I'll leave it out for now. Acceleration is 0 for x and negative 9.81 for y. The initial position, do we know that? Yes, because I'm writing it here. Is that what it said? 1 meter, yep. And that's the y position. The x position is 0 because being dropped from right above the origin. Do we know anything about the final position? Yeah, we know that PFY is 0.15 meters, and PFX is what we're trying to find. Do we know anything about the initial velocity? Okay, so VIX and VIY, we do know both of those, and we're going to get those because we know that at the instant it's released, the ball is moving with the velocity of the bicycle, whatever it's dropped from. And that's horizontal with a magnitude of 5 meters per second. So what are the components of that velocity vector? Positive 5, 0. So 5 for the x component, 0 for the y component. And we don't know anything about the final velocity. So this is it. Okay, is there an equation that works with this? I think the answer is no. So no equation works. So instead, let's try to find time final. Okay, so is there an equation that has time final and everything else in it is listed as known? And I think the answer is this one. PFY is equal to PIY plus VIY times TF plus 1/2 AY TF squared. So 0.15 is equal to 1 plus 0 plus 1/2 times negative 9.81 times TF squared. And so we have positive 4.905 TF squared is equal to 0.85. So TF is equal to plus or minus. Can someone calculate that? So divide 0.85 by 4.905 and then take the square root. 0.416 seconds, and we want the positive one. And now we're back to step 2, I guess. I mean, really, we still know all the stuff we did before. We're still trying to find PFX. We just know one more thing than we did before. Now we know time final. So is there an equation that has PFX in it, and everything else is either listed here or time final? And now the answer is the x component of that same equation that we just used. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus, what was VIX? 5, yep, times time final. What was AX? 0, yep. And so we just have, oh, and we calculated TF. That's the whole point. So 5 times 0.416. And so that is 64. I can't do that. Okay, so PFX is 2.31808. Yeah, 08. Is that what you said? Okay, meters. So if you know you're going to be going exactly 5 meters per second and let go of the ball exactly 1 meter off the ground, put the tape on the floor 2.08 meters away from the cup, and it'll go right in. Any questions about that? Okay. Let's take the quiz.